Stereo. Excuse me. Okay, so in the last section, in section 3.3, we talked about how to quantify acidity using pKa. So that was section 3.3. We talked about pKa values, and I said you should memorize table 3.1. Well, in this section, we're going to look at a way to quantify acidity. And the way that we're going to actually quantify acidity is by looking at the stability of the conjugate base, because we know the more stable a conjugate base is, the stronger the acid that would result after it accepts a proton. And there are four main factors that affect the stability of a conjugate base or a negative charge. And they are, in this order, atom, so the type of atom that carries the charge. The next thing is resonance, so good news, we covered that in chapter 2 in detail, so you know all about resonance. Then induction, and that means inductive effects of electron withdrawing groups, so you can imagine that electronegativity is going to show up there. And then the last thing is orbitals. So whether the charge resides on an sp3 hybridized atom or sp2 or sp. So the way that we remember these factors is using the acronym AREO. And AREO, like I said, it's going to come up a bunch of times in this class. It'll even come up in organic chemistry too, so make sure you understand it as we go through it. All right, so AREO, the first one is atom. And there's two ways of doing this. We're going to look at it in terms of period. So atoms in the same period. So remember that periods are horizontal. So a period in the periodic table. And then we're also going to talk about the vertical columns, which we call groups. So it depends on whether the atom that the negative charge is if the two atoms, are in the same period or in the same group. So let's take a look at two atoms that are in the same period. So it says here we can determine whether an oxygen or a carbon is going to better stabilize a negative charge. So we're going to skip right ahead to number 2 here, okay? We're going to skip number 1. And it says, since carbon and oxygen are in the same period, they are similar sizes. So in this case, the relative stability of the base is going to be based off of electronegativity. Now, which atom is more electronegative? Is it oxygen or carbon? Well, carbon has an electronegativity. That's right. Thanks, Hannah. Carbon has an electronegativity of about 2.5, whereas oxygen is the second most electronegative element on the periodic table. It has an electronegativity of about 3.5, and therefore oxygen is the winner. And so if you have atoms in the same period, it's going to be based on electronegativity. So I'm going to write here, period, electronegativity. Okay, that's what's going to be the deciding factor. And I know that you know that electronegativity increases going up and to the right of the periodic table. However, number 1, we haven't addressed that yet. What if you have two atoms that are different sizes? Because carbon and oxygen are similar sizes because they're in the same period. Well, let's take a look at two atoms that are in the same group. So if we compared the relative acidity of water to hydrogen sulfide, so H2S. Okay, let's compare these two molecules. So which one is more acidic? Is it going to be water or hydrogen sulfide? Well, if we want to evaluate the relative acidity, what we're going to do is we're going to look at the stability of their conjugate bases. So if water loses a proton, you end up with a hydroxide ion. And if hydrogen sulfide loses a proton, you end up with a hydrosulfide ion. So put that here. So now you have the negative charge on an oxygen or a sulfur. And the question is, well, which one is going to better stabilize that negative charge? Well, if you noticed on the last slide, it isn't based off of electronegativity, it's based off of size. And we know that as you go from oxygen to sulfur, that sulfur is going to be larger because you're increasing the principal quantum number as you go down a group. And so since sulfur is larger than an oxygen, it's going to better stabilize the negative charge. So we can say here, more stable base. And if this is the more stable of the two bases, that means the H2S is going to be the stronger acid. All right, so H2S is a stronger acid than H2O, and you can actually see that when you look at their pKa's. If you remember, the pK of water was 15.7. It turns out that the pK of H2S is 7.0, so it's significantly more acidic. If we take a step back to this slide here, so this is what's shown here in the first bullet point. It says the larger the atom, the more stable the negative charge. So size is the most important factor when we're dealing with elements that are in the same group or same family. So we'll put here size is going to be the most important factor when we have atoms that are in the same group with a negative charge. Give me a thumbs up if you follow me on the same period. We look at electronegativity, but if the negative charge is on two atoms that are in the same group, then we look at size, and of course you know that size increases as we go down a group. All right, so there you go. So we've covered atom. So that's A out of area. Now we're going to move on to resonance. And again, I know you spent a lot of time studying resonance. You're probably still studying it. This is chapter 2 in our textbook. And if we compare the relative stability of this base, so we call this an ethoxide, and this one here, which we call an acetate. If we compare the relative stability of those two bases, we cannot use atom to determine which one is going to be the most stable, because the negative charge is on the oxygen in both cases. So we can't use atom. However, we move over to R, and R is resonance. And you remember that from the chapter on resonance that the more resonance contributors we have to the hybrid, the more stable the ion or the molecule is. And so we see that when we have the carboxylate, right, this compound over here, we see that we have two resonance structures, and therefore the charge is delocalized. Therefore, this is the more stable of the two conjugate bases, and therefore its conjugate acid is going to be more acidic. And thus, our conclusion is resonance can stabilize a formal charge by spreading it out. The more stable the base is, so the more resonance structures it has, the stronger the acid that it came from. Somebody asked me a question about the previous rule, the atom rule. It says, if they're both in different groups and periods, does the first rule take priority? I tell you what, Savannah, I'm not going to ask you anything about that. The exam isn't going to ask you anything about it. The quiz won't ask you anything about it, so don't worry about it. I'd say in that case, Savannah, you'd have to rely on pKa. You'd have to go with pKa values. So could I ask you a question where you have to have pKa's memorized, the ones from table 3.1? Yeah, but if I'm asking you to use A, or the A in Aereo, I'll either give you two atoms in the same group or in the same period. Cool? All right, well, let's move on from there. So we've covered resonance. And next, we're moving on to induction. And I know that you know all about electronegativity, and that electronegativity, if I draw a little periodic table here, this is Mr. Dion's shorthand periodic table, not very good. But anyhow, you know that electronegativity increases as we go up and to the right. And so what induction does is, if you remember dipole moments, it stabilizes a formal charge just by having electron withdrawing groups, right? Because electron withdrawing groups, they serve to stabilize a negative charge. So if you were to compare these two acids, this one down here at the bottom, this is acetic acid, and next door to it is trichloroacetic acid. If you look at their conjugate bases, if you were to try to say, is this more acidic or this one? Well, they gave you the answer here on the slide. But if you look at their conjugate bases, right? So if I draw the conjugate base of the acetate or the acetate ion, which is this, and if I draw the conjugate base of this guy, which I don't feel like doing, but hey, it's my job. So let's pencil in all those chlorines, right? You can't use atom because the negative charge is on an oxygen in both cases. You can't use resonance because they both have two resonance contributors. So you go to the next thing, which is induction. And since you have a dipole going this way, and this way, pulling electron density towards those chlorines, it stabilizes the negative charge on the oxygen. Excuse me. If the negative charge is more stable, it means that the base came from the more acidic acid. Is not the best way of explaining it, but it comes from something that's more acidic. Give me a thumbs up if you follow me on induction. So the more electron withdrawing groups we have, generally speaking, the stronger the acid will be. All right, cool. Well, let's take a look at an example of a trend. If we go from acetic acid, so this is acetic acid. You would have seen that many times in Gen Chem 2. And then we call this monochloroacetic acid. Then this is dichloroacetic acid. Then this is trichloroacetic acid. you see that what happens as we add more and more chlorines, that electron withdrawing effect is exacerbated. And so the conjugate bases get more and more stable, and therefore we have more and more acidic carboxylic acids. I'm going to ask you a question here. What if I was to draw this carboxylic acid? So if I put this here, and what if I had, instead of 3 chlorines, what if I had 3 fluorines? 1, 2, 3 fluorines. If you were to compare these 2 carboxylic acids, could anybody guess which one of these would be more acidic? Would it be the trichloroacetic acid or the trifluoroacetic acid? The one on the top or the one on the bottom? Which one would be more acidic? And we're going to use induction to explain it. Yeah. It's going to be the trifluoro, right? Why? Because fluorine is the most electronegative element in the periodic table. So it's pulling electron density away like crazy. And we actually see that manifest in the pKa. It turns out that the pKa of trifluoroacetic acid is about 0.23. So it's significantly more acidic than trichloroacetic acid. In fact, we use trifluoroacetic acid. We have an acronym for that. So trifluoroacetic acid, we call it TFA. We actually use this as a reagent a couple of times in organic chemistry too. Never in organic 1, but in organic 2, we use it a couple of times. Okay, so we've covered induction, and now we're on the last one. So we covered atom, resonance, induction, and now we're on to the very last one, which is orbital. The type of orbital can also affect the stability of a formal charge. Let's think about this. If you have a negative charge on an sp3 hybridized carbon versus an sp2 versus an sp, well, which one of these orbitals is the smallest? The answer is the sp is the smallest of these 3 orbitals. Why? Because it's made from 1 s and 1 p orbital. The other ones have more p's, and therefore they're bigger. And so the idea is this: if you have a negative charge in an on an sp hybridized carbon, it's going to be more stable than one that's on an sp3. Why? Because the electrons are closer to the nucleus, and the nucleus is positively charged. So therefore, they're going to be more stable. Let's take a look at some examples here. If you take a look at ethane, if you draw the conjugate base of ethane, so let me just pencil that down here. We have something that looks like this. All right, then we have a lone pair here, and something that looks like this. So now we have a negative charge on an sp3 hybridized carbon. If we draw the conjugate base of ethylene, we would have the negative charge on an sp2 hybridized carbon. And if we draw the conjugate base of acetylene, then we have a negative charge on an sp hybridized carbon. All right, this is sp hybridized. So the reason why acetylene is the most acidic is because the negative charge that results when you form the conjugate base is going to be closer to the nucleus than the negative charge on the conjugate base of ethylene or ethane. So there you go, based on hybridization. Whichever one has the smaller hybrid orbital, that is the one that's going to be the most acidic. All right, so when assessing the acidity of protons, we generally use areo as the order of importance. So number 1, we always start with atom, ATOM. Then the next thing, we go to resonance. Then we go to induction. And then finally, we go to orbital. So we do it in that order. Okay, so you want to remember it in that order. It's typically helpful to use this order of priority when comparing the stability of conjugate bases. There's an uh-oh here at the bottom. It says, but it's not 100% reliable. There are exceptions. Okay, there are exceptions to the areo rule. I'm only going to go over one in particular, one that you have to have memorized. However, there are lots of them. And so the best thing to do is memorize. If you memorize pKa's, you can you can never go wrong with the pKa, my friend. You can never lose. If you have the pKa value, you can always use that. That's an ace up your sleeve, okay? So memorizing pKa values is the best thing you can do. And as far as areo goes, like I said, there's some exceptions, but there's only one exception that you need to know, okay? And the exception is this one right here. If we take a look at the reaction between this alkyne, so if you remember from the previous slide, this is called acetylene. This is called an amide ion. Yeah, I know there's a functional group called amide, but this is called the amide ion. So if we have a reaction between acetylene or an alkyne, so we have an alkyne and the amide ion, it actually lies to the side of the conjugate base of the alkyne and the ammonia molecule. And you might think, well, this doesn't make sense, right? Because based off of areo, I have a negative charge on a nitrogen. That should be more stable than a negative charge on a carbon, because if you draw the first period, right, you have boron, carbon, nitrogen, oxygen, fluorine, right? So nitrogen is more electronegative than carbon. So this one should be more comfortable with the negative charge. And so the equilibrium should lie to this side, but it doesn't. So this is an exception to the rule. All right, so why is that? Well, it says if we had judged it on conjugate base stability, we would have concluded that the negative charge on nitrogen is more stable than the negative charge on carbon, and predicted the equilibrium to the left, so we would have been wrong. So the conclusion is this. Here's our conclusion. For some acids, you just need to know pKa values because they are exceptions to the areo priority rule. Somebody asked in rule 4 with orbital, would we ever compare a p orbital to an sp3 2 and 1? No, that won't happen because it's not about a p orbital. We're talking about hybrid orbitals, right? A p orbital is not hybridized. All right, so let's move on from there and let's try a practice problem. It says predict which proton, red versus blue, is more acidic in each of these compounds. You can use the pKa's, you can try and use areo. Just, you know, you're a scientist. Try to use everything you have at your disposal to figure it out. If I look at the first one, which is phenol, so I have this proton in red on the oxygen, and then I have the proton in blue on the carbon. Which one of these is going to be more acidic one? Would it be the red one or the blue one? Yeah, it's definitely the red. You could do it with pKa's, right? You could say the pK of phenol for that proton was around 9.9, and the pK here was about 43. So yeah, that's definitely going to be more stable. The next thing is if you look at the atom, I mean, if you use areo, if you couldn't remember the pKa's, and you think about the negative charge on an oxygen, it's going to be more comfortable than a negative charge on a carbon. So you could definitely use areo to solve that as well. And on top of that, you have a whole bunch of resonance structures for this guy, right? If you were to remove this proton, you have no resonance structures whatsoever. The next one, okay, I'll try to expand this here. We have the red proton in the middle, and we have the blue proton on the right-hand side. Which one would be more acidic, do you think? Yeah, I'd say it's the red one too. I'd say this one's going to be more acidic. I mean, even if you didn't have the pKa's memorized, you could use areo. If you draw, let me use my red pen. If you drew the conjugate base that results when you remove the proton in the middle, right, you end up with this, and you can draw a resonance structure where you push the lone pair up on top of this oxygen, and then you could draw another one where you push the lone pair up here. If you ripped off the one in blue, you only have one measly resonance structure that you can draw. This is the only one you have, right? You have nothing else other than that. So here you have a total of 3 resonance structures, and here you only have 2 resonance structures, All right. So again, we can't use atom because the negative charge is on a carbon. We can't, so then we go to resonance, and it turns out that when we rip off the red proton, we have more resonance structures. You could also use the pKa's. We said the pK of the proton of the 1,3-dicarbonyl, it has a pK of about 9. And the pK, this one here, you would just consider this a ketone, right? So this is a ketone proton, and that has a pK of around 19.2 is what it said in the table. So good enough. All right, let's try the last one. We have a proton on an oxygen, and a proton on a nitrogen. Either way, if you deprotonated either of these, you could draw resonance structures. But that's neither here nor there, because if we just think about atom, right, it's going to be the one in red, isn't it, right? Because it's going to have a negative charge on a more electronegative element. I'll just put here, O is more electronegative. And I recommend that you keep trying with this, practice the skill 3.23. Keep going, keep working through them. You can see that sometimes you use pKa, sometimes you use aereo. I can even ask you the exception, right? So all these things are pertinent moving forward in the class. Well, I'm going to move past the section about the relative acidity of cationic acids. I'm going to come back to this either at the end of the lecture today or the beginning of lecture next class. So I'll put here, we'll be back after these messages. No, we'll be back. I want to come back to this section in a little bit. It's based off of electronegativity and just comparing conjugate acids, but we'll come back to that in just a minute or just a little bit. And I wanted to move ahead to section 3.6, where we predict the equilibrium position. All right. So if you have any kind of equilibrium, right? If you go back to your Gen Chem 2 days, remember that's all you talked about? Equilibrium this and equilibrium that for probably 2 months or something. Well, if you're trying to predict, is the equilibrium going to lie to the right or the left? The best thing you could do would be to look at the pKa values of the acid and the conjugate acid. That's the best thing you could do, right? Because the equilibrium is going to lie to the side of the weaker acid. So whichever one has a higher pKa, it's going to be on that side. If you don't have the pKa values memorized, then you can use aereo, and you can evaluate the relative stability of the conjugate bases. So the equilibrium is going to lie to the side of the more stable of the two conjugate bases, right? Because the more stable base is going to come from the stronger acid. So with all that in mind, let's try a problem here. Let me see. Yeah, I don't like that problem. Let's try this problem here. It says predict the position of the equilibrium for the following reaction. We'll try this one and another one. So could anybody, suggest what would be the best way to solve this problem? Would it be aereo or using pKa values in this case? I guess we could try both. You want to? Let's try pKa's first. Who remembers what the pKa of ammonia was? Does anybody remember the pKa of ammonia from the table if you have to go back and look? Yeah, thanks everybody. It was 38. Great. And what was the pK of, just a carbon-hydrogen bond on an sp3 hybridized carbon? You can see there's lots of them here, lots of them in this molecule. If I have like all of these bonds, every single one of these carbons is sp3 hybridized. So if I have an sp3 hybridized carbon-hydrogen bond, it has a pKa equal to 50. Right? So if we label this as our acid, this is our base, right? Because the acid is donating the proton, the base is accepting the proton. This would be our conjugate acid, and this is our conjugate base. So if we compare the pK of the acid and the conjugate acid, the equilibrium is going to lie to the side of the weaker acid. Therefore, the equilibrium is going to lie to the right-hand side. We're only going to have a little bit over here. So we'll say lies to the RHS, the right-hand side. I'm going to draw another one down here. I want you to give it the old college try. Just separate those two. What if we had something that looks like this? So I'm going to draw this plus this. And this is an equilibrium that we looked at earlier today. Let's just try another one. So if I look at this reaction here, I'll give you a second to study it. Could anybody tell me which side the equilibrium would lie to here? Would it lie to the left or to the right? You can use Aereo, you can use pKa values. Would my equilibrium lie to the left or to the right? Absolutely, right? Lies to the right-hand side. Why is that? If we label our acid, this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid. If we look at the pKa of our acid, phenol has a pKa of around 9.9, and water has a pKa of around 15.7, and therefore water is the weaker acid, and so the equilibrium is going to lie to the right-hand side. Maybe I'll just erase this arrow and put a little tiny arrow down there like that. All righty, there we go. So either way, we can use Aereo or we can use pKa values, and we can determine which side the equilibrium lies to. All right, I'm going to skip this question here, and we'll come back to it later. It says, choose an appropriate reagent for this acid-base reaction. So I'll kind of show you how it works. I actually have 4 different compounds and ions on here, and it says, choose an acid from table 3.1 that could effectively protonate each of the following molecules. Well, the reason I'm not a mega fan of this question is because you could use sulfuric acid to protonate anything. But anyhow, we'll come back and we'll take a look at this one in a little bit. Anyhow, I want to cover something with you called the leveling effect. And I know that this concept is covered in General Chemistry 2 because I just finished teaching General Chemistry 2 a couple of weeks ago. So this is something you should have seen in Chemistry 1411. However, I'm not going to put you on the hook for it because you don't cover it in a lot of detail in Chemistry 1411. But the idea is that, let me just kind of expand this here. Let's imagine you have a bottle here, right, that says sulfuric acid on it. Okay, so if it says sulfuric acid, sulfuric acid is a solution of H2SO4 in what solvent? Can anybody tell me? And it's not a trick. If it's the solvent you're thinking of. What's it in? Sulfuric acid. What's it dissolved in? It's in water, right? Okay, great. So what is actually inside the bottle of sulfuric acid? What's actually in there? Let's go over to a blank document. We got time. Let's take a look. If you have a bottle of sulfuric acid, okay, H2SO4, it's dissolved in water. You just told me that. So we know that sulfuric acid is a stronger acid than water, of course, okay? So it's going to be our acid, and water is going to be our base. So sulfuric acid is going to donate a proton. You're going to be left over with the hydrogen sulfate ion plus hydronium. And so hydronium is our conjugate acid, and the hydrogen sulfate ion is going to be our conjugate base. If we look at the pKa's, this acid, sulfuric acid, has a pK of -9. Hydronium has a pKa that's equal to -1.7. So what does that tell you? It tells you that the equilibrium is going to lie hard to the side of the hydronium. You're only going to have a tiny, tiny bit of sulfuric acid molecules in there, almost none. And so the idea is that what the leveling effect is that if you have an acid stronger than hydronium, right? Sulfuric acid is a stronger acid than H3O+. If you have an acid stronger than hydronium in water, based on the leveling effect, all you're going to have pretty much are hydronium ions. You have almost no sulfuric acid in there. And if you're wondering, well, would the same thing apply with hydrochloric acid? Is it mostly just H3O+ and Cl-? Yes, it is. Okay, so when you look at a bottle of sulfuric acid, it's mostly just hydronium ions that are in there. There's very, very little H2SO4 molecules intact, and we call this the leveling effect. Let's go back to our slides. Okay, we go back here. We call this the leveling effect. Where am I? Just bear with me. the leveling effect, okay? So what I said to you was acids that are stronger than hydronium can't be used in water. Why? Because if you take an acid like HCl, which is a pK of -7, it's stronger than hydronium, and you put that in water, the equilibrium is going to lie mostly to the side of the hydronium plus the chloride. It says also bases stronger than hydroxide can't be used in water. Why would that be? Let me just answer it for you because I can't wait to look on the next couple of slides. Let's imagine you had NH2 minus, right? That's a base we looked at earlier today. If you were to combine that with water, okay, water has a pKa of 15.7. It's going to rip the proton off of water to give you ammonia, which has a pKa of 38, plus the hydroxide ion. So what does that tell you? If this is our acid and this is our conjugate acid, the equilibrium is going to lie hard to the side of the conjugate acid. So what that means is that if you have a base that's stronger, so NH2 minus is stronger than OH minus, that means it's not going to work in water because it's going to be destroyed. You're going to have none of that base left. It's going to grab all the protons off of the water and you're going to destroy it. It's going to be converted into NH3. You have no NH2 minus left. And that, my friends, is what the leveling effect is. So if you're wondering, well, what's the consequence of the leveling effect? It says appropriate use for water as a solvent. When can we use water as a solvent? If you go back to your general chemistry 1 and 2 days, you used water as a solvent for virtually everything you ever did in those classes. Water is almost, not never, but it's rarely used as a solvent in organic chemistry. So when can you use water as a solvent? Well, here's a reaction in organic chemistry that you could use water as water as a solvent. So if you wanted to dissolve the acetate ion, could you put it in water? Sure, because can it remove some of the protons? Sure, but this is going to be the weaker acid. Water is a weaker acid than acetic acid, and so the equilibrium is going to lie to the left-hand side. And so it's totally fine to dissolve the acetate ion. We can dissolve that in water. It's no problem. It's an appropriate solvent. So again, the leveling effect is acid stronger than hydronium can't be used in water, and base is stronger than hydroxide can't be used in water. All right, so here's just the exact explanation of what I just told you. I just explained it before I came to this slide. But again, it just shows you the equilibrium between sulfuric acid and water. Where's the equilibrium going to lie? It's going to lie to the side of hydronium because it has a lower pKa than sulfuric acid. And again, the same thing would apply for HCl because it has a pKa equal to -7. And that, my friends, is what the leveling effect is. Now, if you're wondering, well, what's the relevance for me? Do I just have to memorize the rule and that's it? Well, I guess memorizing the rule is one thing that you're going to have to do, but then, and you have to understand the rationale using Aereo or pKa's. But if I gave you a question like this, it says, bases stronger than hydroxide cannot be used in water. For example, we would not be able to perform the following acid-base reaction in water, okay? It's just a straightforward reaction. This is called a dimethylamide ion. This is called 1-pentyne. But anyhow, here we have a reaction between the pentyne, and we see that this has a pKa equal to 25. This is our acid. This is our base. This is our conjugate base. And this is our conjugate acid. And we said that an amine has a pKa equal to 38, right? This is the exception that we learned. Aereo doesn't work here. You have to use the pKa's. But you can see that based off of this is our weaker acid. And so the equilibrium is going to lie to the side of the products. What the slide is saying is this, is that you could not do this reaction in water. If you put this reaction in water, you're gonna ruin everything. The whole thing is going to be destroyed. If you're wondering, well, why is that? Okay, because we said that if you have a nitrogen, an N- base, it's stronger than a hydroxide. So this is a stronger base than hydroxide. So it's going to grab protons off of water, and you're going to destroy all of this. It's not going to be in your reaction mixture anymore. Let me prove it to you. So what's going to happen is this is going to react, let me put it like this, with water, okay? And you're going to end up with this compound where you have an amine plus OH minus. So now I'm going to put this in a red box, okay? Just like a movie box, okay? So if we look at the pK of our acid, the pKa is equal to 15.7. If we look at the pKa of our conjugate acid, the pKa is equal to 38. Which side is the equilibrium going to lie to? It's going to lie to the side of the products. So it means you're going to have destroyed all of this. So water is not an appropriate solvent for this reaction based on the leveling effect. All right, give me a thumbs up if it makes some sense to you. You're thinking, yeah, I guess this does make some sense. So if you're wondering, well, what kind of solvent could I use to do this reaction in? A hydrocarbon that is made, so a hydrocarbon is something that's made only of carbon and hydrogen. If you use something like this, 1, 2, 3, 4, 5, 6, we call this hexanes, right? In hexanes, since every bond in here is between an sp3 hybridized carbon and a hydrogen, right? The pKa is equal to 50. And so hexane is not going to react with the amide ion. It's not going to react in any way, shape, or form. And so this would be, we could use the Drake meme, right? Good solvent, bad solvent, okay? All right, there we go. So that, my friends, is the leveling effect. You're like, yeah, I do feel like I'm leveled now. All right, let me show you a couple more things, and then we'll take another short break here. If this one has been annoying you since you first saw it, excuse me, the difference in pKa between these two alcohols, excuse me, this one, ethanol is 100 times more acidic. You can't use aereo here, can you? You can't use atom, you can't use resonance, you can't use induction, and you can't use orbital. Well, there's got to be an answer, doesn't there? It actually lies in the structure of the conjugate base. If you look at the conjugate base of terbutanol, we call this tert butoxide. I've mentioned it a few times already. And if you deprotonate this, you end up with this ion. We call this ethoxide. So why is the ethoxide more stable? Why is it a more stable base? It must be more stable because it results in a more acidic alcohol. Well, the answer lies in steric effects, okay? Or all those CH3 groups, or what we call methyl groups, that are surrounding the carbon that has the oxygen attached to it. Notice that in the tert butoxide ion, you have all of these groups, I'll use my blue pen here, that are surrounding the negative charge. Whereas in the ethoxide, you only have one little group kind of that's surrounding that negative charge. And so what it does is when you have less groups attached to the carbon with the oxygen on it, it allows more solvent molecules to surround that negative charge and stabilize it via probably a dipole-dipole effect, okay? Whereas when you have something with three or what we call alkyl groups, or all these different groups on here, it's so bulky that you can only get a few. You can only get a couple of solvent molecules, and that's what it is. It's based off of steric hindrance. The more steric hindrance you have around the negative charge on the oxygen, the less solvent molecules can come in and stabilize that negative charge. All right, let's look at one more section before we take another break. And this section deals with counter ions. It's a very short section. You see, it's only one slide, okay, section 3.9. If you're wondering, you know, when you, Mr. Dion, you've drawn a bunch of equilibria like this, and you had negative charges, but you had no cations. There was no sodium or lithium or potassium. Like, how do you have just a negative charge hanging out in thin air? Well, the answer is you don't. There's no such thing. It doesn't exist. So if I go back, let me just go back and find an example to prove it to you that I've been doing this up. We'll just look at this example here. Here you have a negative charge here, and you have one over here. I have no positive charge stabilizing that. You guys have studied enough chemistry to know that doesn't exist, right? There has to be a positive charge around there somewhere. Well, if you're wondering, why do we leave them out all the time in organic chemistry? The reason, and we don't always do it, but the reason we do it most of the time in organic chemistry is because those cations are just spectator ions. What does that mean? They're there, they balance out the charge, but they don't actually participate in the reaction. So since they're not involved in the reaction, we like to just leave them out. Why? I don't know. I guess you could say we like to simplify our lives, or you could say organic chemists like to get the maximum amount of work done for the minimum amount of effort. Either one is perfectly fine. And if you're sitting there thinking, well, I want to include cations, I suppose you could, but the textbook won't do it. Okay, in the solutions very rarely, unless it's really required or something. So we often just leave them out in this class. Do you guys remember writing out molecular equations and then complete ionic equations and then net ionic equations in Gen Chem 1? Does anybody remember doing this? And then you would cancel the spectator ions as you went from complete to net. Yeah. Okay. So if you're wondering, is it the same thing as that? You cancel those ions out. It's the exact same thing in this class. Exact same thing. No difference whatsoever, man. It's identical. All right. So that is kind of the rule. It says at the bottom, what does he say here? It says counterions are often left out of an equation because they generally don't play a significant role in reactions. Are there exceptions? Of course there are. But in this class, even in organic too, like I told you this morning, talking about Lewis acids and bases, there's very few situations where I'm going to bring up a cation and say, oh, this is important for some reason. So I can tell you right now, don't stress about them for quiz 3, really. As long as you know they're spectators, that's good enough for me. All right.